1A is pretty short. There's not a lot of details to it. We are talking about space figures, and another name for a space figure is just a 3D figure. So we're going to be talking about three-dimensional figures. First thing you need to know is what this word means. Okay, that is polyhedron. And that is a space figure, or we can say a 3D figure, whose surfaces are polygons. Okay, that's what a polyhedron is. So every face, every surface of the figure is a polygon, a triangle, a rectangle, a square, a hexagon, a pentagon. As long as it's a polygon, you put all those together, you get what's called a polyhedron, okay? So I'm just gonna show you the different pieces that come into play with polyhedrons by showing you a rectangular prism. This would be what we call a rectangular prism. All your faces are rectangles on this. There are three different components that we're going to talk about, okay? The first one is where three or more edges come together. In other words, three or more lines are coming together. So like this right here is called a vertex, which we've talked vertices before, right? Plural, like I said, is vertices. So there are some number of vertices on any given prism like this. But it has to be where three or more edges meet. Okay, that's a vertex. Then we also have edges, and since we're talking about edges, we should know what they are. An edge is just where two faces come together, so two polygons come together. So this right here is called an edge, and it's just where two faces meet. Okay, and then the last thing is a face, which is what we were just talking about. Probably should have done this in a different order. So this right here is called a face. It's just whatever polygons you're working with. Your face is always going to be some polygon. So in this case, our face is a rectangle, but you can have faces that are triangles. You can have faces that are hexagons, pentagons. Any polygon can be a face of a polyhedron, okay? So with those, we are going to talk about numbers of faces, of vertices, of edges. So let me draw you a quick picture here. Let's say we have that figure. If you just draw a triangle and then extend from the top vertex another side, and then just the dotted line is kind of your back hidden piece. Let's say this is R, S, T, and U, okay? I want to know, in this picture, how many faces, how many vertices, how many edges do you have? So how about vertices first? How many vertices do you see in this picture? One, two, three, and four. Okay, we have four vertices. How many edges? Right, you have 1, 2, 3, 4, 5, and 6. So there's 6 edges. And then your faces. There are 4 faces. And the faces are a little harder to represent, like how you would shade them in. So if I'm talking about the back face, right, there's the back. There's this kind of left side triangle. That's 2. There's this right side triangle. That's 3. And then the bottom would be 4. Okay, so you have 4 faces there. So with that, there's this guy, his name is Leonard Euler. It looks like Euler, E-U-L-E-R. And he came up with a formula to be able to figure out the faces or the edges or the vertices if you know 2 of the other 3 things that we're talking about. So Euler's formula, spelled like this, E-U-L-E-R. Okay, that's Euler's formula. What he discovered was that if you take the number of faces and add to it the number of vertices, it will always equal the number of edges plus 2 in any polyhedron. Okay, so F plus V will always equal E plus 2. So if you look up here and try that out, faces plus vertices should equal edges plus 2. 8 equals 8. That is true. Okay, so we're going to use Euler's formula sometimes to solve for a missing number, sometimes just to verify that the numbers we have are correct. Okay, so let me give you another picture here. Example 2. They're going to ask you how many faces, how many edges, how many vertices. This picture is not the easiest to draw. Basically, it's a pyramid with an upside down pyramid underneath it, you could kind of say. Do your best if you're drawing along with me. But it looks something like this. Okay, so there's this pyramid, but then underneath it, is this wigging out on me? I keep seeing like flashes. No? Okay. Underneath, what? Okay, so a pyramid on top, a pyramid on bottom is essentially what this figure looks like. And I want to know how many faces, how many edges, how many vertices. So faces, edges, and vertices. Okay. 8 what, Matt?
8 faces.
There's 8 faces, right? So if you look at the triangles, there's 4 triangles on top and 4 triangles on bottom. So there would be 8 faces. How many edges are there?
10?
Not 10.
Oh, 6.
No. There's 12, right? So if you think 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12. That's all of your edges. So there's 12 edges. And then how many vertices? There's 6. There's 4 around the edges, 2, 3, 4, and then 1 on bottom and 1 on top. So there's 6 vertices. Now here's the deal. If they're asking you for how many there are, you always want to double check that your numbers make sense. So it should work out that faces plus vertices equals edges plus 2. So if you plug that in, faces plus vertices, so 8 plus 6 should equal 12 plus 2, and 14 equals 14. So we know that checks out. Okay, so these would be the correct values. Questions on that?
No.
Okay. One thing maybe to note up here, this Euler's formula is for a 3-dimensional figure, which is what you see there, right? 3-dimensional, it's got depth, it's got height, it's got width. He also came up with a formula for a 2-dimensional figure. So I'm going to tell you that one too. We use this one less, but it does get used. It says in a 2D figure, okay, the formula instead is F plus V equals E plus 1. What I mean by a 2D figure is if we have the net for some figure, right? That's two-dimensional. If I take that figure and I lay it out flat, how many faces, edges, and vertices am I going to have? So let's just say for a cube, okay? If I were to draw the net for a cube, and I'm going to run out of space there. Hi there. Thank you. Sarah. Oh, this is lunch. Not yet. She's leaving later. All right, so say we draw the net for a cube. That would look like this, right? Remember nets? That was our very first lesson, I think. You should be able to tell me right now how many faces, how many edges, how many vertices we have. How many faces do you see? 6. There's 1, 2, 3, 4, 5, and 6, right? So our faces would be 6. How many edges? A lot. I always think it's easiest on these just to draw it out because you can just trace them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So you have 19 edges. And then your vertices, again, easy to label them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? Huh? Okay, so if that's your setup, you should be able to say faces plus vertices should equal edges. Now it's plus 1 instead. So just remember, if it's laid out flat, you're adding 1. If it's three-dimensional, you're adding 2, okay? That comes out to 20 equals 20, so it checks out, so we know we have the right numbers. Yes, ma'am?
For a way to, like, find, like, the vertices or whatever, if you, like, find the faces and, like, the edges, can't you just, like, already add the 1 to, like, the edges and then just subtract it from the faces?
What? Right. Yep. Right now, the way I'm using it is more as like a check method, like make sure we got the right numbers. But assuming you have the right numbers for the first 2, you can always find the third one that way. Yeah. Any questions on that? That is the first lesson. Good old Euler.